Okay, so we can generalize all these different optical elements as the element that collects bundle of rays coming from some source and then redirecting them so that they pass through some point. Okay, here in this picture you see this is some optical element. Okay, it could be any kind of shape like parabolic or some other shape. We don't need to worry about that for now, just some general optical surface, and it collects all these rays and it redirects all the rays at this point P. Okay, this is the source and this is the point where all the rays are collected. And using the Fermat's principle, we know that light travels through the shortest possible distance and in shortest possible time. So, if all the rays meet at the same point, that means they will travel all these different paths in same time. Okay, it will take same time to travel through this path as compared to that path, as compared to that path. So, all these will travel the paths at the same time, during the same time, so that they meet at that point, right. If it takes like some x second for this one, it will also take x second for this one, x second for that one. So, they will take the same time so that they meet at the same point. We can also have another kind of optical element which redirects the rays. So, it is redirecting, this optical element is redirecting the rays. Okay. So, these are the rays coming from the source and hitting the optical surface, and the optical surface is redirecting the rays, and this optical element redirects the rays in such a way that these rays appear to come from some other source, some other point P. Okay. Although it's originating from S, but if you look from this side, it will appear to come from P. Okay. So, we can have these two types of optical elements. Okay. So, one redirects the ray at point P and the other one redirects in such a way that they appear to come from point P. So, now those days people try to derive different kinds of surfaces or equation for different surfaces that satisfy these conditions. Okay. So, one of the derivation was done by René Descartes, the great mathematician and philosopher. So, he did this derivation. So, he chose a parabolic surface. We have this, not parabolic, sorry, elliptical surface. So, this is an elliptical surface, and in this elliptical surface we have this point S, that is the source of some light source. Okay. And the light coming from point S hits the surface of the ellipse at this point x y, and then it is reflected back, and the light goes through point P. Okay. And this S is so any ellipse has two foci or foci, whatever you say, right, or if it is one, we call it focus. So, it has this focus point and that focus point. So, the light originates from this focus and it goes to the other focus. Okay. And the property of the ellipse is that the distance of any point from one focus plus the distance of that point from other focus is always equal to 2 times this distance, or I mean 2 times this semi major axis. Semi major axis is this distance. Okay. So, from the middle point to this point is semi major axis, which is A, and semi-minor axis is from this middle point to this top point. Okay, so that's B, semi-minor axis, and this distance plus that distance would be equal to 2 times the semi-major axis. That's always true for any point, whether you choose this point or some other point like here. If you choose that point, okay, so this would be your R1 and this would be your R2. So for this point also, R1 plus R2 would be 2 times A. Any point you choose on this ellipse, you get the same result. Okay, if you want to choose a point here, that would also work. So this would be your R1 and that would be your R2, and the sum of those two distances would be 2A. Okay, so that means, now using the Fermat's principle, let's see if I can erase that. Okay, that means if I consider these two paths and let's say it takes time t to go from here to here. Okay, that if I choose some other point, then it should take the same time if it goes through the point P. Okay. Also, if let's say this is R1 prime, and the path difference between R1 prime and R1 is delta R, then the path difference between this one and this one also would be same. Okay, because the sum is always constant, right? So that means if you, whatever part you subtract from this one to get this one, you have to add that part on that one to get this one, to make this constant. Does that make sense? Because the sum of these two lines are always same. So you see here, this one is shorter than that, right? So let's say this one is delta R shorter than that one. That means this one needs to be longer than that one by the same amount, because we need to make it constant. Okay, just to fulfill this condition for the ellipse. So let's say you choose two rays that are pretty close to each other, like this one, okay, and that one. It's not very straight, but let's assume that it's straight line, and let's consider the small part here, yeah, small section of this ellipse. So it will look like this. So we are considering this small portion, and if you blow it up or zoom in, you will see this straight tangent line. Okay. Now, so we have two rays, this one and this one. They are pretty close to each other, and this one is R1 plus dr. So dr greater than that, like I said before. That means this is the distance, this is the difference between the two paths. So this is R, and that's R plus dr. So that much is the difference, like I said here. So these two rays would be slightly different by some distance, and the equal distance would be the difference for these two also. That means these two also will be different. So if this one, let's call this 2 and this one is 1, if 2 is dr distance greater more than this one, then its reflection, this 2 would be dr distance shorter than this one, because we want to again fulfill this criteria. Okay, to make the sum same, this needs to be dr less than this 1, or in other words, this 1 needs to be dr more than 2. Does that make sense? No? Again, the sum of this one and this one is always constant, right? If this length is that much bigger than that, that means this needs to be, or this one needs to be that much shorter than this one. Okay. So, that means this distance would be equal to that distance, because both are the change in the path. So, this distance would be equal to that distance, both are dr and dr. That means in this triangle, in any triangle, if the two sides are equal, this side is equal to that side, then this is isosceles triangle, and the base angle of isosceles triangle are equal. Okay, so this angle would be equal to that angle. So this angle theta 1 is the angle of incidence, and theta 2 is angle of reflection. It's not exactly angle of reflection, but it's glancing angle. Okay, let's say we measure this angle of incidence with respect to the surface, then this would be angle made by the incident ray with the surface, and theta 2 is the angle made by the reflected ray with the surface. So, oops. So, this ray and this ray are parallel. That means, if you have theta 1 here, this would also be theta 1, right? If you have two parallel rays and a line passing through that, so that means if this is theta 1, that would also be theta 1. So, corresponding angles. So, same thing here. So, this angle would be equal to that angle, and these two are also parallel, this one and this one. No, what happened?
Wait, where are they parallel?
They are not parallel, but if you consider them to be very, very close, you can consider them to be parallel, more or less parallel. Exactly, not exactly parallel, but you can consider.
Basically negligible.
Yes. When these points are far apart, when this point and this point are far apart, you can consider that the ray is more or less parallel. So that means this is theta 2 and that's also theta 2. So that means this angle is theta 1 and this one is theta 2, and from the isosceles triangle these two sides are equal. That means theta 1 must be equal to theta 2. Okay. So that means this kind of surface could be used for the purpose of reflecting light, because it satisfies the condition of reflection. Okay. So this kind of surface is good for reflecting light. So now, what exactly is the shape of that surface? We want to show that. Okay. Mathematically, we want to get an equation that represents this surface. So for that, let's do this treatment. So let's go back to our picture. So let's look at this picture and see that again our surface is ellipse. So ellipse has r1 plus r2 is equal to 2a. So this r1, if you consider this right triangle, Okay. So, this distance from here to here is x. So, this x is x coordinate, that distance. Okay. And this is middle point. So, from this point to the middle point is semi major axis, that is semi major axis. Okay. And this distance is s. Okay. So, from the focus to the this edge is s. Okay. So, by using the Pythagoras theorem, this is a right triangle. So, this distance would be square root of this distance, this height is y, okay, y squared, plus this distance, the base. Okay. So, base is, what is base? So, base is this whole distance x minus s. So, x minus s is the base. So, that is squared plus height squared, y squared, that is that distance. Same thing here. So, this R2 would be, using the Pythagoras theorem, this whole thing is, let us see. So, this whole thing is no, not that. So, from here to here is p. Okay. So, from this point to the origin is p, and from here to here is x. So, that means, so we have this to be x. Okay, let us use different color just to make it distinct. So, this is x, and that whole thing is p. That means, this distance would be what? So, from p to the origin is p, and from this base to this origin is x. That means, what would this distance be? Yeah, p minus x. So, that means, base squared p minus x squared plus height is y squared. Okay. So, we have R1 is that and R2 is that. If you take the sum of these two, that should be equal to 2a. Okay, that is what we have here. So, this is R1, that is R2, and their sum is 2a, and which is also true, which is also 2a is, it is a little bit messy here. So, let us maybe erase this. So, 2a is from here to here, which is this distance, which is this s plus s plus p. Here, let us do it. Here is. So, this one is s. Okay, same distance here and here. So, this is s, same here. So, that is also s, and from here to here is p. Okay. So, that means, this whole thing is p plus s, which is what we have here. So, 2a is p plus s. So, 2a is R1 plus R2, which is also p plus s. Now, assume that p goes to infinity. Okay. So, this means our ellipse is very, very long compared to the height. We have a long ellipse, and compared to this distance, this is pretty short. So, that means we can neglect y goes to 0 when p goes to infinity. When this point is far away from the origin, we can consider this y to be negligible. Okay. So, that means, if I neglect p, then I will get, this is same here on the second term, sorry, not p 0, I meant to write that. I want to write this y to be 0. We are considering this y to be 0. So y is 0. So we have the same term on the right side, on the left one. So for this one, p minus x, so this goes to 0. So that would be what we will be left with. Okay, and then on the right side we have p plus s. Okay, that's that. The only thing we did here is when that is infinity, p is infinity, y goes to 0. So we can do a little bit of rearranging here. So this p and p will cancel on right and left, and when I take this x on the right side, I get x plus s here. Okay, this is exactly same down here, and this x goes to the right. And you can do the little bit of math here. So square on both sides, you get x squared minus 2xs plus s squared plus y squared. I'm squaring on both sides, so x squared plus 2sx plus s squared, and using the a minus b squared formula. So x squared and x squared cancel, s squared and s squared cancel. So we have y squared, so that's y squared, and this one take it to the right, add with this one, so you get 4sx. Okay, we get this equation, and this equation explains the shape of this thing, shape of this reflecting surface, which is the equation of parabola. Okay, so that means for this spheric surface we can use a parabola. So a parabola can be used as a reflecting surface. And again, spheric means with something that is not perfectly spherical. If you have a perfect sphere, then we have learned about this spherical meter. This spherical meter is a part of this spherical surface, but here we are talking about some aspheric surface that is not perfectly sphere, not spherical. Okay, and that is a parabola. So we can use a parabola as a meter, which is what we use in lots of reflectors. Okay, and the parabola has the center of symmetry at 0, 0. Okay, like here. So let's see the picture here. So another picture is here. So this is the parabola, and it has center of symmetry at 0, 0, which is also called vertex. So that's center of symmetry means this half is identical to that half. Okay, so that means this is the center of symmetry. Like for a human being, this is the center of symmetry, because along this line, this left half is similar to the right half. So that's the center of symmetry. Like here, this point is the center of symmetry, and this point is focus where all the lights converge. So you can have two cases here when you use parabolic meter. One is you can have a source at focus. If you have a source at focus, not necessarily that's always true, but let's say you have a light source at focus. If you place a light source at the focus, then the light rays will hit the parabolic meter, and they will go towards infinity with the rays parallel to each other. So these rays would be parallel to each other whenever the source is at the focus point. And also, let's say you have light rays coming from some infinitely far source. Your source is somewhere at infinity here. When the source is at infinity, the light rays are parallel, and if they are parallel, then the light will converge at focus. Okay, so these two are the conditions that are satisfied by any kind of parabolic meter, parabolic reflecting surface. Yeah, some kind of light. You put a light.
The first one's a flashlight, right?
Yeah.
That's
So you use this in a flashlight. Yes. So you have a flashlight. You have this parabolic reflecting surface. You have a some kind of bulb there, and these bulbs, the light coming from this bulb hits the mirror or this reflecting surface, and these light rays go in the parabolic in parallel lines, parallel rays. So yeah, this is the reflecting surface on your torch light. And this kind of mirror is used. I have never seen this kind of thing in this country, but in many other countries they use this for heating water. So they have this parabolic mirror, okay, and then they have a water tank or something, and the light ray coming from sun, these light rays are focused at that tank container, and that hits the water. Yeah. Same thing with the disc. What is that called? Signal disc antenna.
Oh, the satellite dish?
Yeah, satellite disc. Yeah. So basically, you collect the waves coming from a source at infinity, and then you have the receiver here, and that receiver gets the signal reflected by the parabolic satellite or the disc. Okay, so this is about the reflection. Now, what about the refraction? Okay, so what kind of surface will satisfy the refraction, or what kind of surface we can use for refraction? So the purpose of refraction is again to either converge or diverge the rays. So in this case, we are converging the ray. So we have this source here. The source is traveling along this path. It's so difficult to write a straight line on PowerPoint. So that's the ray traveling along that line, and the function of this refracting surface is to bend the ray so that the ray is converged at some point here. Now, if it is going through the center, it will just go straight, okay, without bending. And if the rays, both this ray, upward ray and the bottom ray, they meet at the same point, then it will require that both the rays complete this path at the same time. Okay, meaning if it takes x second to go along this direction, this path, then it should also take same time along the bottom one, because they need to meet at that point at the same time. Okay, so that means the path, although is different, but they will take the same time. Now, we can use a term called optical path length, for which the equivalent time would be same. Okay, so what that is let's consider that for for any path, we know that speed is defined as distance over time. So we can write distance, or we can write time is equal to, rearranging that, we can get distance over speed. So for any path, we can write t is equal to d naught over v. Okay, so this is in any medium. In any medium. Now, if we want to write this in terms of refractive index, then we can use this formula. So we have refractive index is given by c over v. So we want to replace this v in terms of refractive index. So that would be c over n. So, I can replace this by c over n. Okay. Now, if I multiply t and c, this would be the path traveled in vacuum, okay, not in the medium, because c is the speed in vacuum and t is the time taken to travel the path. So, that would give you the path traveled in vacuum. Okay. So, that means if we consider this t times c to be d, then our path traveled in vacuum would be given by this formula, and this is what we call optical path. Okay. Oops. So, optical path is given by n times d naught, it is a refractive index times d naught, and we can find optical path for any medium. Okay. So, we can write this path in terms of optical path, okay, by using this formula. So, so we know from Fermat's principle that the time it takes to travel this distance should be same as the time it takes to travel this distance, because they need to meet at the same point at the same time, right. If it takes longer to this one than the bottom one, then they will meet at this point at different times, which is not what we want. We want to get all the rays at the same time. So, that means this is the time to travel along this upper path, let us call this T2, and this is the time to travel along this bottom path, let us call that T2 T1. Okay. So, this is time T2, that is time T1, and they are equal. So, we have two sections for upper path. We have this section outside the medium and section inside the medium. So, this section and this section. So, that's so the time to travel this section would be given by what is the time to travel this section? R1 times, what should we call it, T2 1 maybe, and then this one is R T2 2 maybe. So, that is the time, and this time would be given by d over v. D is R1, okay, here R1 is the distance, and V is, because it is vacuum or air, so we can write this C here. Here this one would be distance R2, and that is V, because this is a medium, so I cannot write C here. Okay. So, the total path would be total time would be then R1 over C plus R2 over V, or let us say this is not a vacuum. Okay. It seems like we are not considering this to be vacuum. Let us say this is medium 2 and this is medium 1. I mean, I can consider this to be vacuum, but for a general case, let's not consider that to be vacuum. Okay, so let's just consider that this is some other medium with refractive index n1, and this is the medium with refractive index n2. So I can write this as n R1 V2 is C over N1 refractive index in that medium, and R2, this V2 is here using this formula, C over refractive index, C over N2. Okay. So, that is 1 over C R1 N1 plus R2 N2. Okay. So, which is this one, N1 R1 N2 R2, and I have 1 over C here. I can do the same thing for this bottom also. Okay. I will get 1 over C here, and I will get that term, and I cancel C and C, and I get that expression. Okay. This comes from the fact that it takes same time for the light to travel from the upper medium and the bottom medium. Okay. You do a little bit of math, and then you get that expression. Okay, I will take maybe 2 more minutes because we are out of time. Now, we can use this triangle and the other triangle, and then write this R1 and R2 in terms of the other variables. Okay, let's erase that. So, R1 is square root of this base squared. This base from here to here is S. Okay, the distance from there to there is S, and from this origin to here is X. Okay, that means this whole distance, this base of this triangle is S plus X, which is that. Okay, so this is S plus X squared, and height is y squared. That's the Pythagoras theorem. Okay, so that's R1. Same thing with R2. I can do the same thing. So this take the triangle. I want this base, and that base would be P minus X. Okay, so this whole thing is P, and that much distance is X. So that means this base would be P minus X, which is what we have here. And then, so that's P minus X squared, and then the height squared, height is y. So that's that. Okay, and on the right side, we are not doing anything. It's just as it is. Okay, so we got this equation, and all the points on this surface that satisfy this equation is called Cartesian ovals. Okay. So this surface is what we called Cartesian oval that satisfies this equation. Now, let's do one more thing, and then we'll finish this. So exactly same thing we will do here also that we did in the previous one. We'll consider this P is far from the origin. Okay, it's like that. So when this P is far from origin, then this y could be considered to be negligible, okay, compared to that P. So this y is very, very small. So when we do that, then this term will go away. So this will go away. So we'll be left with, so this will also go away. We'll be left with whatever is left after removing y. Okay, so I rewrote this equation. So this will go away. Let's see. P minus X. So we are not using y0 here. Oh, okay. So P minus X. S plus X. Okay, I think maybe we'll continue this next time because we don't have time, because you guys have to go to next class, right? Do you guys have class after this? You don't have class? Okay. Why you don't have class today?
You're done with all, you
all the presentations. Okay. Oh, okay. Oh, okay. So I see. Okay. So here, now I see why we have. So here in this term, we do not have p. Okay. We have p here. So in comparison to this term, we can neglect this one. But since we don't have p here, we cannot consider this to be 0. Right. This is true only when we are comparing this with p. Okay. That means I can only get rid of this term, but not this one, because we don't have p here. This is still valid. So that means that the y is 0 here in this term. We'll still have y here. Okay, and we do a bunch of rearranging here, so you cancel that term and that term. So then you will be left with that, and then you rearrange just like before. You square both sides and then rearrange the terms. Okay, you get this kind of equation, and this equation could be written in this form. Okay, considering a to be that and b to be that. This is, do you guys know what this equation is? This is equation of hyperbola. Okay, equation of hyperbola, which is like this. Okay, or like that. So this is hyperbola. So that means our refracting surface that is not spherical is hyperbola. Again, we are talking about, why it's doing that? We are talking about, come on, aspheric, okay, not spherical. Any aspheric surface that could be used for refraction has to be hyperbola. Okay, we'll stop at this point. We'll continue this next time.